Hi, I'm Jaehwan Seong from Korea. In Korea, today I will presenting our research on tracking algorithm for hazardous area in construction site using PTG cameras. This study proposed a smart safety monitoring system that can adapt to dynamic condition in real-world construction sites, overcoming the limitation of static surveillance systems. Oh, yeah. Here is an overview of today's presentation. Introduction, proposed frameworks, experiment, result, and conclusion. As you know, the construction site is inherently high risk due to the heavy equipment or complex workflows or long project duration. In 2023, over 1,000 fatalities occurred in U.S. construction sector, and more than 26,000 injuries were reported in Korea. A large portion of these incidents occurs in static hazardous areas such as trenches, edges, or material storage areas. While these areas are predictable, manual supervision is inefficient and error-prone, especially under fatigue or limited visibility. This has led to growing interest in computer vision-based safety monitoring systems. Recently, PTG cameras which alone pan, tilt, and zoom are increasingly used for site-wide surveillance. However, they bring a critical challenge. When the camera moves, the previous defined hazard area becomes misaligned or distorted in the video. For example, you can see the image hazard like an opening or material storage areas may shift in appearance in position depending on the camera's angle or zoom levels. This distortion can result in incorrect safety judgment. Therefore, to properly utilize PTG cameras, we need a tracking algorithm that can adapt hazardous areas location in real time according to camera's motion. Our goal is develop a vision-based tracking algorithm that can dynamically update hazardous areas without relying on external sensor. That the system we propose offers first on camera pose estimation using only image data. Second, dynamic reconstruction of hazardous area as the camera moves. Third, robust performance under rain, fog, or poor lighting. Finally, the lightweight structure that can be applied in small and medium-scale sites. The core mechanism of the frameworks is the homography transformation to track the hazardous area across different camera's viewpoints. As the PTG camera moves, the system estimates its post and reproject the hazardous area accordingly. To improve the stability, we also define strategies for selecting reference images and pre-processing input frame. The framework consists of the three main components, each playing a role in different tracking approaches. First is camera pose estimation. To estimate the transform matrix between images using feature matching. It forms the basis of approaches 1 and 2, enabling reprojection to hazardous area. At this research, I used X-feature models to estimate the camera pose. Second is visual place recognition to check whether the current scene is the same location as the originally defined hazardous area. If not, the system suspends tracking. This is critical in approaches 3, 4, and 5 for handling scene changes. The applied repair types are twofold. One, based on the feature match quality using X features, and the other based on the mixed repair results. Third is the molecular depth estimation. Extract depth from the single images to enhance feature robustness under weather and occlusion. It assists repair and tracking in approaches 3, 4, and 5. And I used the mixed yes. First, we built a virtual construction site using Unity. It simulates realistic conditions, structures, equipment, dynamic lighting, and weather effect. Static hazardous area were pre-trained and predefined and used as ground truth. After validating performance in this virtual environment, we applied the best performing approach in 20 real-world videos from 13 construction sites. We make five different tracking. We evaluated five different tracking approaches. Approach 1 is frame-to-frame transform. Approach 2 is reference image-based transform. Approach 3 and 4 are added prepare to post-tracking when scene changes. Approach 5 is hybrid method that dynamical switches between prepare types based on feature match quality and mixed prepare result. This approach 5 achieves the best accuracy and stability. For performance evaluation, we used the IOU between the ground truth and tracked hazardous area. We also assess activation and deactivation accuracy during scene transition and stability over time based on video length, short, mid, long. And these metrics help evaluate both tracking precision and long-term operational reliability. This is the result of each approaches and this one. In virtual environment, approach 5 achieved that average IOU is 0.8627 and IOU 80 is over than 87% of the frames and stable performance across all video duration. And real-world test, the algorithm achieved the approach 5 algorithm achieved on average IOU of 0.7 for 3, showing it is sufficiently accurate for field deployment. The slight drop is due to the real-world complexity like lighting variation, occlusion, and motion blur. To summary, we developed a sensor-free tracking algorithm for PTC camera that can dynamically follow hazardous areas. It was validated in both simulated and real environments and showed high potential for real-time construction site safety application. However, this study is currently limited to 2D tracking in real construction site. As you know, the hazardous area often exists in 3D space. So we plan to extend our method to support 3D object tracking. We also aim to integrate this system with worker access detecting algorithm and further improve the performance under complex site condition. This is my reference list, and thank you for listening.